Time to get back to astronomy. Hey, Leslie. And we're all here. Man, too bad I don't have a quiz for today since we're all here. So, last class period, we used the lamp here. And we saw that there was a fundamentally different thing when we looked at this compared to this. That is, when we looked at the lamp that's like a neon lamp. This is exactly what neon lamps are, except for the gas inside is different. It didn't look at all the same as when we looked at this filament. So what was different about the two?
Well, like this separation of the colors instead of just like
Separation of colors? What were you going to say, Clay?
the way the colors were like, well, one was like to the side, the other one was like little lines. I can't really describe it well, but it was different.
Well, we call it a line spectrum, so that's that's a good description because that's what we call it. So we saw distinct lines here, whereas we saw a continuous spectrum here. Something fundamentally is different about the way the light is produced. And I will have to turn on the projector for you to see these slides. It sometimes escapes me, that logical step. So today we want to learn a little bit about why those are different. And you're probably thinking to yourself, why is this important? I'm taking an astronomy class. Well, when we look at stars, we're looking at the light coming from them. And if we understand how the light is produced, then we can infer what's going on in the star from what we see in that light. So first we'll start with an atom. While this is coming up here, I'll go to the slide. So when it comes up, we'll have a picture of an atom, at least in my memories, right? Tell me what an atom is like. Oh, no, this here is a prism. I have a prism there as a throwaway slide. Prisms separate light. We use glasses, right? The glasses we used here, it usually goes without saying you shouldn't write on them, but these are apparently nerd 4 eyes, according to a student. That's actually a student wrote it like the first or second year I got them. There was a guy who suffered a traumatic brain injury, and he just thought it was hilarious. So these here are made by putting a whole bunch of little slits. It has a whole bunch of lines, thousands of lines. And when the light passes between the slits, it does what we call diffraction. It bends. Light bends around corners. Pretty shocking, because if I step outside the door and go around the corner, you're not going to see me, right? But you know that sound waves go around corners. If I go outside the door, step around the corner, and speak, you're going to hear me. Because the sound waves bend around, we don't think light does. Light does because all waves do. But light has such a short wavelength. Remember we talked about the wavelengths of visible light between approximately 400 nanometers, that's 400 billionths of a meter, to 750 nanometers. Very, very short wavelengths. Whereas the sound waves have much longer wavelengths. The sound waves coming out of my mouth are going to have, let's say that my frequency is about 600, we're going to go 700 hertz. Just, it's in that ballpark. Easy, because 700 hertz it's a standard frequency for a person to talk. The speed of sound in air is about 340 meters per second. So let's just round up to 350 meters per second since I made it up. And we learned the relationship between wavelength and frequency yesterday, or last class period, that frequency times wavelength is equal to the speed. So that means if the wavelength for sound is equal to, or excuse me, I'm trying to find the wavelength. The wavelength is the speed over the frequency, which would be 340, let's say roughly 350 meters per second, divided by a frequency of 700 hertz. What did a hertz mean? It's a measurement of frequency, but it has to mean something. It means a cycle per second. So instead of writing hertz, I'm going to replace that to 1 over second. So we see, we're going to have some units canceling here. We have the 1 over second there and the 1 over second there cancel. 350 divided by 700 The wavelength for the sound I make is about 1/2 meter. That's really long compared to the wavelength of light, which is on the order of, like I said, a couple hundred billionths of a meter. So the light does not bend around the corner the way we can see. So these are using something, light's bending around these slits. The prism is using what we call refraction. Refraction is bending of light when it goes from one material to another. The wave bends because you have a different wave speed. Because light will go slower in the prism than it does in air. And it turns out that different colors of light have different speeds in the glass. So the blue light has a much slower speed than the red light. Well, much slower. Has a slightly slower. Has a slower speed than the red light. Because it has a slower speed, it bends more. And so we have a spreading of colors in a prism. That's how prisms work. We don't need to know the physics of how a prism works or the physics of how this works. What we do need to know is we have good ways that we understand how we can separate the different frequencies or the different wavelengths. So we can separate the light. And here's the light we see coming from the sun. Now this would be one very long spectrum with blue on one side and red on the other. And to make it fit on the page, they just put line on top of line on top of line instead of having a really, really long one. Or squeezing it in so you couldn't see all of those gaps. There's a lot of gaps, aren't there? The sun isn't giving us a completely continuous spectrum like this did. It has some missing colors. And so those missing colors are reminiscent of this, because this only gave us certain colors. And so to jump to something we'll get at the end of today's lecture, that spectrum we're seeing from the sun starts with this. It starts with producing a continuous spectrum because it's hot. We call that incandescence. So the sun is a mass of incandescent light. Okay, incandescent gas. I said it wrong. It's a song we'll learn later. So the sun is a mass of incandescent gas. It's giving off light because it's hot. But that gas is absorbing the exact same colors that you would see emitted from this. So we can learn about the atmosphere of the sun by examining those gaps, which is pretty amazing. And you see there's a lot of gaps there. And what that gives us is a lot of information about the atmosphere of the sun. So emission spectra is what we saw. Now that does not have helium, and this is a helium lamp that we use. But these are the spectra that you would see from different gases. Now you see sodium. Sodium, most of you think of sodium as, well, table salt has sodium chloride, right? But sodium is actually a metal. It's a metal that doesn't like water. And when I say it doesn't like water, I'm absolutely lying. It loves water. It loves water so much that it blows up if you put it in water, because it undergoes a very rapid reaction with water. So that's why I said it doesn't like it, because it has the big reaction. But it has the big reaction because it loves it. But you can take that sodium metal and you can vaporize it. You can put it into a vapor form and have a tube with sodium gas. And then if you make electrons go flying through that sodium gas, they will excite the gas that gives off light. And we're going to learn today just a little bit about atoms so we can understand how they give off light. So that sodium spectrum, that if you have those specific lines, you know it's sodium. Anywhere on Earth, whether it's in vacuum, you can't really do it in there because you have all kinds of other gases. But anywhere on Earth, you're going to get that same spectrum for sodium. So if you see that spectrum, you know it's sodium. And you notice each one of these has a very distinctly different spectrum. Now you see some things you say, well, it does look similar. I mean, you've got these two lines. Those look similar to those two lines. But if you take the whole, no, there's not going to be any confusion. And so we say this is kind of like a thumbprint. Each element has its own thumbprint. It has its own spectrum, and you don't get them confused. If you see that spectrum, you know you have that. And so when you look at the sun, it's not just one gas, you have many gases, and the trick is to deconvolve them, to separate these lines in the sun come from this gas, these lines in the sun come from this gas, and separate them out and say, we have this much strength of absorption from this gas and this much strength of absorption, and go through. That's how they determine what's going on in the atmosphere.
So it's like decoding.
Yes, it's very much decoding. And it's not simple, and it turns out it gets even more simple. Or more complicated. We have the thing, the very last slide is on the Doppler shift. I'm not likely to get to the very last slide, but if we do, it turns out that when something is coming toward you, well, you have this experience. If a car is coming toward you and its horn is on, you hear, and then when it passes, what happens? Meow. We call that the Doppler effect. The Doppler shift is a shifting of the frequency when something passes. The reason is when it's coming toward you, each crest of the wave is actually closer together because the source was moving the same direction that the sound was. So the sound didn't get as far away from it in the time between one crest being produced and the next one. So the wavelengths are compressed in space and it's coming toward you. It's moving away from you, it's just the opposite. You have the same thing occurring with light. Now it is phenomenologically different for light because light travels at the speed of light, and it doesn't have a medium. You can have light travel through a vacuum. Because of that, it's a different equation, but you still have the Doppler effect. So this spectrum is based on something stationary. Something's moving. All of those lines are going to shift a little, and we can calculate how much they should shift. And so when people were looking at the spectra from stars, at first they were like, this doesn't match anything on Earth. Maybe they have different atoms out there or something. And then somebody else said, hey, if we were to apply Doppler shift, these shifts would all match hydrogen. They would all match hydrogen with a certain speed. And so all of a sudden, boom, hey, we can do it. We can calculate how fast the star is moving toward us or away from us by how much those lines are shifted. And then we can, once again, see all of the different lines for the different atoms and determine the composition. Now, while I'm on this, somehow remind me, you guys read recently about Jocelyn Bell. She's got a married name, it's like Burnell or something. Yes, no? She was just awarded a $3 million prize for her advances in astronomy. It's actually a really incredibly sad story to me. It's not because she's a woman in this case. It's because she was a graduate student. She is the person who discovered pulsars. You guys have heard of pulsars, right? She discovered pulsars. Nobel Prize. Not to her. Because she was the graduate student. Who gets credit? In the textbooks, we always talk about Jocelyn Bell as the one who discovered the pulsars, but her professor is the one who got the Nobel Prize. Yeah, she was a graduate student when she discovered them. Yeah, that's kind of the way it is.
Why? Even to this day.
Well, okay. One of the things we're going to talk about, you say to this day.
No, it's like, does that still
Pretty
happen?
much, yes. The professor gets the credit because
We discovered something.
here's the reason why the professor gets the credit. Yeah, you discovered something wrong? No. The professor gets the credit because the professor is guiding the student's research. And so the professor says, why don't you study this? The student finds something really cool. The professor says, yay, I did it. It's probably a little better now, but because there's a lot more communication in this world. But that's the way generally it's gone. That's the reason, because the professor is the one that was guiding the work. I'm not saying it's right. We'll see another example in today's, like the slide that I thought was going to be the first one. It's coming up, trust me. Everybody knows about the Rutherford experiment, but it wasn't done by Rutherford. It was done by Marsden. Nobody knows who Marsden is, but Geiger was working for Rutherford, and Marsden came in to work under them. And the guy here said, hey, I think that Marsden's ready to do his own research, and Rutherford said, well, have him do this. He did it, and it made Rutherford very famous. Okay, sorry, I went off on, anyway, she got a $3 million prize, and she said, I don't need the money. I am donating all that money to Women in Science Foundation to try to get more equity for women in science, because she certainly believes it was because she was a woman, at least in part, that she did not get recognition for her, well, did not get the Nobel Prize for her very own research. There are other fine things that would go on. Fred Hoyle, that's his name. Fred Hoyle's research got a Nobel Prize, and he didn't get a Nobel Prize because he rejected the Big Bang Theory. So, the planetary model. He rejected the Big Bang Theory because he said there would have to be a God for the Big Bang to occur, and he was an atheist. So, coming to this, I'm just letting you think about that for a few minutes.
Yeah, it didn't click, but then now it clicks. Okay.
Yeah.
It's like, what?
Yeah, he was an atheist, and that's why he rejected the Big Bang Theory. So, the planetary model. The planetary model is the model that Rutherford came up with. So I just told you the research was actually done by an assistant in the lab, by Marsden. Basically, he was what we would call now, I think, a postdoc. He had finished his education, and now he was working with a researcher to, make some credibility for himself. And they gave him this experiment. It's called the Rutherford gold film experiment. They were studying actually radioactive particles. And they were shooting these alpha particles, which are helium nuclei. Of course, we don't know what helium nucleus is at this point in the class. They didn't really either. But they were shooting these particles that they had determined things about, and they're shooting them at a very thin foil of gold. Why gold? Because gold is malleable. You hit it with a mallet, and it squishes instead of breaking. And so you can make very, very thin gold. And so they made a very thin sheet of gold, and they fired these particles at it. And what they thought material was that you had previously, Thomson had discovered that there were electrons in matter. And so they said, okay, it's like a plum pudding, or I like to say oatmeal with raisins. You have the oatmeal is just this positive charge that's spread out everywhere kind of uniformly. And then you have the raisins that are the little electrons, the negative charge. And so the expectation was if you have this really thin gold, the alpha particles are probably just going to go straight through. But on the off chance they hit an electron, then they will just have tiny, tiny deviations because they knew the alpha particles were way more massive than the electrons. And so Marsden does the research. He comes back and says, those alpha particles are going all over the place. Some of them bounce straight back. And as Rutherford said when he went on the circuit to talk about this, it was as if you were to shoot a cannonball at a piece of tissue paper, and when the cannonball hits the tissue paper, it bounces back at you off of the tissue paper. That's how shocked they were at the outcome of this experiment. And so they said, that model can't be right. It can't be right that matter is just positive charge spread out uniformly with little negative electrons. There must be a very massive center in there. And so he came up with this model, the planetary model, that says you have a nucleus at the center and electrons orbiting circles. Now, this is specifically for a hydrogen atom. Hydrogen has one proton in the nucleus and one electron orbiting it. Different atoms have different numbers of things in the nucleus. In fact, you have the periodic table back there. The first item, top left, is H. And you see H has, inside the box in the top right corner, 1. That's because it has one proton in the nucleus and one electron orbiting it. You go over, the next element is in the top right corner, helium, and it has 2 because it has how many protons in the nucleus? 2, right? The number in the top right corner tells you how many protons in the nucleus. So if you go down there, below helium you have neon, 10 protons in the nucleus. So those numbers, we call them the atomic numbers, and they tell us how many protons are in the nucleus. Now, the nucleus also contains neutrons, and so the mass is the bottom center number. That tells you, if you round it off to the nearest integer, it tells you how many protons plus neutrons are in the nucleus on average. Those are taken on the average of all of them because you have variation in the number of neutrons. And for an atom to be neutral, it would have the same number of electrons as protons. Now, with this planetary model, look, we're studying astronomy, we have the planetary model for an atom. The planets, well, what do the planets do with regard to the sun? They revolve around, they orbit around them. It was known at this time, this was like 1913. They knew that the planets didn't do circles, right? Copernican model, long gone. Everybody understood Kepler's elliptical orbits. And yet, the planetary model says that the electrons are doing circles around the nucleus. That's a model. What is a model?
Just something to base it on.
It's a framework to help you understand it. So that's the planetary model, that the electrons are doing circles. Very quickly, they realized there were problems with this. Niels Bohr came on over and was working with Rutherford and said, well, we've got some serious problems here. How can we modify it? And so they came up with a quantum model, the Bohr model, that says that electrons, well, the Bohr model says electrons are doing circular orbits, but the orbits can only have certain energies. Can't have any energy or any randomly selected energy. That's like saying if it was a planet, the planets can only be 1 astronomical unit from the sun or 2 astronomical units, but couldn't be anywhere in between. It can only have certain distances from the sun. It doesn't make sense for the planets, right? But with Bohr's quantum model, that was the outcome, that you only have certain distances that they can orbit from the nucleus, and only certain energies that the electrons can have in orbit. Now, once again, the Bohr model answered a number of problems with the planetary model, but it also introduced more problems. And so that's not what we believe anymore either. What we believe is the quantum model, the Bohr model was a quantum model, as you heard me say. But the quantum model that we believe now says that the electrons are orbiting the nucleus. How? We have no idea. Now, some of you have probably taken, how many people have taken a chemistry class, high school or college? Okay, all of you. You guys all learned about s orbitals, right? What is the shape of an s orbital? When I was in high school, I thought that an s orbital meant that it was doing a circle. It's not. S orbital is a spherically symmetric volume within which you have a high probability of finding the electron. But the path it's taken, we have no idea. So our understanding has evolved quite a bit, but we still show pictures of a model that matches the Bohr model. Right? We start with the planetary model, then go to the Bohr model, because it helps us understand the ideas, even though we know they're not what's going on. So if we go to a helium atom, the second one up there, the helium atom has 2 protons in the nucleus, but it also has 2 neutrons. Protons, pro-positive. I am pro-Oakland Raiders. Fan of Oakland Raiders. I could say I'm neutral toward, I don't know, the Cleveland Browns. They can win a game, they can lose a game, I wouldn't care. Neutrons are neutral. What was that?
Unless it's against the Raiders.
Unless it's against the Raiders, well, yes. That goes without saying. So the neutrons have no charge. The protons have a positive charge. And then electrons are not called negons. The electrons are called electron because that is Greek for amber. Duh. Because of Ben Franklin just randomly said whatever the amber has, we're going to call negative. And so they named the particle after amber, and it has a negative charge because Ben said it would. So the electrons have negative charge. I just have to point out, there were good reasons for proton and neutron and electron different. So we have the negative electrons going around the nucleus in some unknown fashion. Because there are two positive charges here in the nucleus, there are two negative charges orbiting around it, so it's electrically neutral. You have equal amount of positive and negative, so the net charge is 0. You can take an electron off. If you take an electron off, then you have more positive than negative when we say it's a positively charged ion. So ion means that the atom has a different number of electrons than protons. It's still going to be helium as long as it has 2 protons. Now, there are different isotopes. Does this matter to you? No, probably not. But it does matter to scientists. Isotopes have the same number of protons, so these are all isotopes of hydrogen. They all have 1 proton. But they have different numbers of neutrons. So hydrogen is used, strictly speaking, for 1 proton, no neutrons. Deuterium, if it has 1 proton and 1 neutron. Why deuterium? Because deut means 2. Has 2 things in the nucleus. Tritium, because tri means 3, obviously, has 3 things in the nucleus, 2 neutrons and 1 proton. Now, talking about that Bohr model, remember, this is not what we believe, but it's still useful to talk about. And the Bohr model works for the hydrogen atom, surprisingly enough. Well, close enough. Bohr said that you have different energies available, only distinct energies though. And so if an electron moves from one energy state to another, you can't just make or destroy energy. It has to come or go. And so if you have an electron that goes from a higher energy level to a lower energy level, it's giving off energy. It's kind of like if I take this meter stick, if I drop it from my hand, when it hits the table, the energy difference that it has from here to here, what kind of energy am I talking about when I talk about its energy here versus its energy here? Potential. The potential energy difference has to go somewhere. While it was falling, it was going to kinetic energy, but when it hits the table, what's going to happen? It'll stop, and energy will go in the form of now, that's not the only place it goes, but it's the easy one to talk about. That sound you heard was from the energy that was transformed from the potential energy here, kinetic energy, and then into sound energy. Also, energy went into heat, making molecules move faster. So with atoms, Bohr said, when the electron falls to a lower energy level, it's going to have energy conserved. So if an electron goes from, let's say, here down to here, then it's going to have some energy that's released. He said that's just going to be released in the form of light. And so the light that we saw from this lamp has an energy equal to the difference in the energy levels of the electrons in the atoms. And theory and experiment match up. It appears to be true. It's been tested and tested over and over many, many different ways. And so we believe that. We don't believe the Bohr model, but we believe that statement that there are only specific energies available to the electrons as they orbit the nucleus, and if an electron falls from a higher energy level to a lower energy level, it will give off light. We call the light a particle, a photon, with energy that's equal to the difference, equal to the energy difference. So now if you look at this, it says red spectral line going from n equals 2 to n equals 1. And it says blue-green spectral line going from n equals 5 to n equals 3. Is that right? No. No, it's going 5. I was looking at my line for some reason. My line is not the one that was marked on there. Going from n equals 3 to n equals 1. And then it has violet spectral line going from n equals 4 to n equals 1. So the violet line See, I have red now, so I should color. Well, they're colored already. It's just hard to tell the violet. Here's a better picture. This picture shows energy drops. So what we have here is N equals 1. That is the innermost energy level. N equals 2. I must have been reading that previous page wrong because they should have all ended on N equals 2. No, I wasn't reading it wrong. It's just drawn wrong. That's good to know. This picture on the right is correct. When you have electrons falling from like N equals 2 to N equals 1 or N equals 3 to N equals 1, those are really big energy drops. And because of those really big energy drops, all of these give off ultraviolet light. So that Lyman series is ultraviolet light. Anything that ends at N equals 1 is ultraviolet. Hence why I said I must have been reading the previous picture wrong, went back and looked. No, it was just labeled wrong. Because you aren't going to get anything that's red, blue, green, or violet going to N equals 1. They're all ultraviolet. It turns out the energy levels for the Balmer series are largely visible. And you get to the Paschen and the Brackett series and the Funt, if you want to go to the next one. Those are infrared. So the actual discovery of these lines, everybody could see in hydrogen, those Balmer lines. Those were the first ones discovered. Called the Balmer series because Balmer, I think he was like a high school or grade school teacher. He was a teacher. He recognized a pattern and came up with an equation that gave you the wavelengths for the different lines in the visible spectrum. And then as instruments became better and they were able to see the ultraviolet light on their instruments, then Lyman found an equation that was just like Balmer's equation, except for one number, that would give you the ultraviolet lines. And then Paschen came up with an equation to give you infrared lines, and Brackett another one, and Funt another one. And actually, there's more than just those. But now we have a very strong understanding of where these lines come from. So the emission lines are from electrons falling from a higher energy level to a lower energy level. I showed you a picture of the sun's spectrum. The sun's spectrum is not at all the same as this. So clearly we cannot say, the sun's spectrum is this. But we can now take this information and we can go back and figure it out. So we have, these are actually Kirchhoff's laws for something, I don't remember the names. But if you're viewing a star, there are 3 different options for what you can see. First, if there is no atmosphere, you can see a continuous spectrum because the sun is giving off light because it's hot. So that would be like looking at this with no atmosphere, no molecules between you and the star. Unlikely to ever have no molecules because the stars always have an atmosphere of their own. But that would give you a continuous spectrum. Now, if the light goes through a cloud of gas, that cloud of gas has atoms with electrons at certain energies. And if light comes in and the light has an energy that's exactly equal to the energy difference between a state that has an electron and a state that the electron could jump to, then that light can be absorbed. If the light's energy is anything other than the perfect gap, it cannot be absorbed. So only specific wavelengths or specific frequencies can be absorbed, and they're exactly the same ones as can be emitted. Because absorption and emission both have to be going from one energy state to another. So you're going to have this gas here absorbing the lines that indicate what gases it has. So you look at this and you see a continuous spectrum with dark lines. We call this an absorption spectrum. Because we're seeing the absorption of those spectral lines. So if you're looking through a cloud of gas, you can see information about the gas actually superimposed on what you get from the information from the hot object. Remember from the end of class on Wednesday that we had the luminosity, the total amount of light given off is proportional to temperature raised to the fourth power, and that the peak wavelength is inversely proportional to temperature. So you can look at the continuous part of that spectrum and determine the temperature, and you can look at how much light there is to get an idea of luminosity. You have to determine the size to really do it. But then what about the last viewing? What if you are, there's a light bulb in this projector. And if I look out here and there's a cloud of gas, since the gas was absorbing energy from the light and making electrons go to higher energy states, those electrons are going to do what everything else does. You raise it to a higher state, you let go, it falls down. And so those electrons are going to fall back down and give off light again, but that light's going to go in a random direction. So you're not filling in those gaps because the light's going in random directions, not going the same direction as the original light. But if you look at the cloud from a different angle, you will see that faint light that's being produced by the electrons falling back down. And so that's the bright line spectrum shown down below. So depending on how you view a star, you could see a continuous spectrum, the absorption spectrum, or this bright line emission spectrum. Question, Mira.
So in general chemistry, we learned that the continuous spectrum was caused by solid, and then the bright line spectrum was caused by gases. Is it different than in astronomy in this case? Or?
Well, the sun has a continuous spectrum, and that's caused by gases. It's very dense gas. Well, very dense. It's not that dense, but it's denser. Hey, this is the last slide. I'm finishing early? God forbid. Don't get too excited here. Final thing is the Doppler effect. The Doppler effect, you can see in these pictures, if the source is moving, you have, the star in the picture on the right, left. Picture on the left. You have a stationary source, and it's giving off waves, and you have the waves are traveling at a constant speed, and so you have, after one period, the period being the time for it to go through one cycle, you have, here's one wavelength away, 2 wavelengths away, 3 wavelengths away, 4 wavelengths away. Those are all concentric spheres. And so if you're standing here listening, you're going to have a peak, another peak, as they come to you. They're all separated by the same time that is the period that it was emitted. So you're just going to hear the pitch that it's producing. But here it's moving. And so it started out, notice this had numbers opposite of the way I was numbering, because it's saying the first wave that is sent out is out to here, the second wave is sent out is out to here, the third one is out to here, the fourth one's out to here. So now here, you have the first wave was emitted when it was here, and that's making this big red ball. And then the second wave was emitted when it moved here. And so because it moved, you have the ball is centered on a different place. The third one centered on here, the fourth one centered on here. But then what you notice is if you're here, those are much closer together. Traveling at the same speed, you're going to hear them coming to you much closer together. Hence, you're going to hear a higher frequency because they're going to be coming at you more per second. If you are on the opposite side, if you're up at the top where it says to observer C, then they're much farther apart. You're going to hear them spaced out more. That's going to be a lower frequency. And if you are over here at the side, the spacing actually is still going to be the same. Somebody had a question a second ago. Leslie.
So what are these circles here?
These circles are
real here.
The circles are the shells of a wave that was emitted at a different time. So you have the first wave that's emitted. I've got to change color if I'm going to write inside there. So this is the second wave, the third wave, and the fourth wave. I started to put a 4 there.
Kind of like a ripple effect?
Well, what you're seeing is the ripples. If this was on water, that's exactly what you're seeing. Is you take a picture, and these are the ripples you have. And so the second one would be like if you have something traveling over the water that just goes ping, ping, ping every second. So it only taps the water every second. And then you have the ripples that go out from each one of the taps. And so this is saying, here's where tap 1 occurred, here's where tap 2 occurred, here's where tap 3 occurred, here's where tap 4 occurred. And each one of these spheres are at the center is where that tap occurred. Right, to use the water for his analogy. And so you have the waves are much closer here. They're all coming at the same speed, so if they're much closer, you're going to hear them boom, 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 when they were actually, the taps were boom, 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 boom. If you're over here, they're very spaced out. And so this shift coming toward you is to higher frequency, which means shorter wavelength. When it's coming toward you, lower frequency, longer wavelength, if it's going away from you. Now that effect, like I said, it's a different equation, but it still occurs with light waves. And with light waves, if it shifts to a higher frequency, what color is on the high frequency edge of the visible spectrum? Blue. That's what you said, right? Yeah, yes it is. Blue or violet. And so we call it a blue shift if something's coming toward you because the color in the middle of the visible spectrum will shift toward blue. Whereas if it's moving away from you, it's shifting to lower frequency. What color is on the low end of the frequency spectrum? Red. So it's a red shift if it's moving away from you. And that shift, like I said, you can mathematically calculate it. I didn't bring the equation out here today. I just wanted to get the phenomenon out here. Now with the time, I should have brought it out. I don't have it memorized. I'd have to look at it, which is kind of silly because I think it's just it's a very simple equation. I don't want to say what I think it is because if I'm wrong, then I'll feel embarrassed. So this is important in astronomy because, like I said, now we can look at stars and the spectrum don't match what they would be on Earth. Using the Doppler shift, we can say, okay, we've got these spacings that look kind of like hydrogen. If we use the Doppler shift, what speed would it be? There, they all lock in at the right speed. And then we can determine how fast a star is moving toward us or away from us. Now, I'm going to ask this question. Don't look at it funny. Does it make sense to say the star is moving toward us or away from us? Right, we've been kind of clear that the sun is not going around us, that we're going around the sun. Make sense to talk about the star moving toward us or away from us? Yeah, it does. It does. It's the right answer. Because are we stationary? No, we're not. Is that star stationary? No, it's not stationary either. We have a relative velocity. The two are either moving toward each other or away from each other, is what we get with the Doppler shift. And you can arbitrarily choose which one you want to treat as relatively stationary. So, we say, well, we're going to treat the Earth as stationary. Well, it's not. It's going around the sun. The sun's going around. Yeah, but for our purposes, we'll treat the Earth as stationary and that star is moving toward or away from the Earth. You could have just as easily said that star is stationary and the Earth is moving toward or away from it. Nobody cares. It's the relative velocity that's important. I'm going to stop there. You guys good with that?
Oh, yeah.
Okay. Oh, yeah. Clayton's totally down. Eli talked to me, and I realized that I had made a new Moodle page and didn't have old tests posted, so now I have lots of old tests posted. Now keep in mind, we're using a textbook that I haven't used before, so those tests aren't going to perfectly represent what's in the textbook, but they do well represent the kind of questions you're going to see on the exam. And you've got lots of examples to look at.
So would you say that's probably one of the best ways to study is to review stuff from the book or whatever, and then
Yeah.
study it?
I always recommend read the chapter summaries. Make sure you understand what's in the chapter summaries. I try to test over only things that I've spoken about in this class. In general physics, there might be stuff that I didn't talk about in the theory, because they're doing more problems in class and less talking in class. So make sure you read those chapter summaries. If you're 100% confident I never talked about it, it probably won't be on the test. A lot of times people don't remember everything I've talked about though, so that's why I had to be 100% confident I didn't talk about it. And you can always go back and watch them on YouTube if you want to check. All right, have a great weekend.